Okay, so let's continue with our discussion of projective varieties. All right. So what we will do is recall from the previous lecture that we are taking K to be an algebraically closed field. So we always at least when I define the projective space, I don't need this. And in principle, according to the most general version of algebraic geometry, which is scheme theory, in fact for defining projective space, K need not even be a field, it can even be a ring. But then let's not go, we are not working in that generality, but we assume that at least we are working with fields, and since we are going to do geometry, we are working with algebraically closed fields. Okay, so at least for the initial part, K just need be a field, it need not even be algebraically closed. So you know we have projective n space, this is projective n space over K. Okay, and what is this? This is it is a quotient of the affine space, the affine n+1 space, modulo an equivalence. And what is the equivalence? The equivalence is you identify points on a line. Of course, I want really non-zero points, so I throw out the origin and then I go modulo an equivalence relation. Okay, and what is this equivalence relation? This is the equivalence relation that identifies 2 points if they lie on the same line passing through the origin. In other words, this is just the space of lines in K n+1. Okay, and so you have a natural map K n+1 to Pn K n+1 minus 0. This is the punctured affine space to projective space. There is a natural map which is the quotient map. Okay, you can think of, so you can think of every point being sent to its equivalence class, and the equivalence class can be thought of as a line. Okay, so you send a point with coordinates lambda naught lambda n to the line passing through to its equivalence class, which is the line passing through lambda naught etc lambda n and the origin. Okay, this is the same as the equivalence class of that point lambda naught etc lambda n, where the square bracket denotes equivalence class, and this is also the same. It is also written in this form. It is written as lambda naught semicolon dot 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 lambda n, where this colon is to be thought of as a ratio, and we put square brackets to say that this is a set of n plus 1 scalars which have this given ratio. Okay, so in other words, what it means that is that, you know, if I multiply this by any non-zero element of k, okay, which means I multiply each entry by the same non-zero element of k, then the line will not change, alright, and the equivalence class will not change, okay, and this also will not change, namely there will be the same scalar multiplied through each of these entries, and the rule is that the idea is that whenever you have this colon, you can cancel off a common factor. So this is the same as t lambda 0 t lambda n for every t not equal to 0 in the field. Okay, so that's because if you take t lambda 0 to 3 through t lambda n, that also lies on the same line joining lambda 0 lambda n through the origin. It defines the same line, so it's the same equivalence class and it's the same point, but the idea here is that whenever you have a ratio, whenever you write a ratio as a is to b, you also write it as ta is to tb. So so the ratio a is to b is the same as the ratio ta is to tb, okay, and you can cancel the t off from the ratio ta is to tb to think of it as a ratio a is to b. That was this is for the case of a ratio of 2 numbers, but then this is a ratio of n plus 1 numbers, okay, and that's the meaning, I mean that's the reason for this notation. These are called homogeneous coordinates, okay, they are called homogeneous coordinates because you can cancel out a common divisor, alright. So well, I have now the point is that we would like to do geometry on the space. So first of all, you know, the starting point is always to first make it into a topological space, and there are 2 ways to do it, okay. So I'll tell you one way. The one way is, of course, use the notion of quotient topology, which comes from topology itself. That's because the space above is actually the affine space, affine n plus 1 space, which is punctured at the origin, okay, and this is a Zariski topology, okay. So this is a topological space and this is a surjective map from a topological space onto another set, okay, and then you can make this into a topological space by giving this what is called the quotient topology for this map, okay. What is that quotient topology? It is the open sets here are precisely those for which the inverse image under this map are open sets here, okay, and similarly for closed sets, okay. So so what we do is that Pn can be made into a topological space in 2 ways. Number 1, use the Zariski topology on an plus 1 minus the origin, okay. An plus 1 minus the origin, which is the punctured affine n plus 1 space, is an open subset of the affine n plus 1 space, and any subset of a topological space automatically gets a induced topology, okay. So this has an induced topology from the bigger space, which is the whole affine space, okay, and so this has that topology, and you can use this Zariski topology to give the projective space the quotient topology via the map pi. You think of pi as a quotient map because it is quotient by an equivalence relation. after all what is projective space? Is the space of lines. What are the lines? They are the equivalence classes under this equivalence relation. So this is a set of equivalence classes, and you always call a map that goes from a set to the set of equivalence classes a quotient map, and you call this set of equivalence classes as the set of you call this the you call the quotient of the the quotient of the given set by the given equivalence relation. So this affine space here is being this projective space is here being thought of as the punctured affine space modulo going mod this equivalence, okay, and going modulo this equivalence is geometrically the same as looking at lines, okay, and every equivalence class here is a line there passing through the origin, okay. So of course when I say space of lines in Kn+1 I should say through the origin, that is important. If I simply say space of all lines, that is not correct. I meant space of lines in n+1 affine space through the origin, right. And okay, so this is a standard thing in topology. Whenever you have a topological space and you have an equivalence relation on that, then you can go to the set of equivalence classes. There is a natural surjective map which associates to every point its equivalence class, and then you can always give the quotient, the set of equivalence classes, a quotient topology using that map, okay, and we can follow that. And what is that? That is a subset W in Pn is open respectively close if and only if pi inverse of W is open respectively closed in the space above, because in the space above, which is a punctured affine space, you know what closed or open means, okay. Open means it is a complement of a closed set, and a closed set means it is an algebraic set. So a closed set here is an algebraic set in the affine n+1 space with the origin removed, okay. That is what closed sets here are, right, for the induced topology. So this is one way you can give this quotient topology, and you see in this quotient topology always in the definition of the quotient topology automatically it ensures that the quotient map becomes continuous, because you are saying that a set here is open if and only if the inverse image is open. So automatically if a set is open, then its inverse image becomes open, and that is the condition for verifying the continuity of a map, okay. So when you give the quotient topology, automatically the map becomes continuous, okay. What is the other way of doing things? The other way of doing things is you try to indigenously define the Zariski topology on the projective space, okay, and how do you do that? You imitate what you did for the affine space, okay. For the affine space, how did we define the Zariski topology? We defined the Zariski topology by defining closed sets, and what were closed sets? They were sets of common zeros of a bunch of polynomials in the right number of variables. Now what you do is you just adapt the same definition, okay, but now you say that you look at common zeros of a bunch of polynomials, but not just any polynomials, but polynomials are homogeneous, okay, because if a polynomial is not homogeneous, then it doesn't guarantee that if it vanishes at one point of a line it will vanish at other points of the line passing through the origin, okay. So what I am trying to say is that when we defined for example a closed set in An or An+1, of course this is sitting inside An, I mean An+1, and how did we define a closed set here? A closed set here was, well, we took a polynomial in n+1 variables, alright, and then not one polynomial but several polynomials, a collection of polynomials, and look at the common zeros and define such sets to be closed sets here, okay. But the problem is that if you take a polynomial, okay, in n+1 variables, trying to say that it vanishes at a point here is a little tricky, which means effectively you are trying to say it's a you must think of it as a polynomial, okay, which vanishes on a point here corresponds to a line here, a line in the affine n+1 space passing through the origin. You want a polynomial to vanish on a line, okay. Now that won't happen unless the polynomial is homogeneous, okay. So at least I should say that at least if the polynomial is homogeneous, you have hope of the property that if it vanishes at a point on a line passing through the origin, then it will vanish on the entire line passing through the origin, okay. So that is the reason that when you define the Zariski topology on projective n space, you look at homogeneous polynomials, and you imitate the definition of the Zariski topology on affine space. While in affine space the closed sets are given by common zero loci of a bunch of polynomials, in projective space the closed sets or the algebraic sets are given by common zero loci of a bunch of homogeneous polynomials, okay. So so here is the second definition. Define the Zariski topology on Pn to be the one for which the closed sets are given as the common zeros of a collection, a subset of homogeneous polynomials. In the all the functions on the affine space above, which is just identified with k x naught through x, okay. So so you can define another topology on the projective space. This is the Zariski topology on the projective space, which imitates it's also given by common zero loci of a bunch of polynomials, but in this case we consider only homogeneous polynomials, okay. And mind you, homogeneous polynomial means that in the variables, if you multiply each of the variables by t, then that is if you substitute for each variable a constant multiple of that variable, okay, the same constant multiple, then that constant comes out with the power, it can be factored out, okay, and that power that comes out is called the degree of homogeneity of the polynomial, okay. So the fact is that actually I think it's a good point to tell you one more thing. There is in fact one more way of getting the topology on Pn, okay. So I'll tell you what that one more way, there is yet another way. Okay, so there is yet another way of getting the topology on projective space, okay. And of course, what I'm trying to tell you, I'm just going to tell you that you define, there are three ways of defining the topology on projective space, and they are all the same, okay. They are all going to give you the same result, all right. So what is this yet another way? This is the standard way in which you think of a projective space as being gotten by gluing n+1 copies of affine space, okay. So you see, I'll tell you, well, let me put it as 3 in continuation with this via the gluing of n+1 copies of an. Now, so I have to explain what this means. So what we will do is, let me do the following thing. So you take projective space, okay, take projective space, and the points in the projective space are written in terms of homogeneous coordinates like this, okay, and then what we will do is, let us look at for each of the and for each fixed position, look at all those coordinates, okay, for which that particular coordinate does not vanish, okay. So what I mean is, you define ui to be the set of all points with homogeneous coordinates lambda naught through lambda n such that lambda I is not 0. You define ui like this, okay. This is for I equal to 0, 1, etc. up to n, okay. You define these sets, alright, and well, you know, you must guess that these sets are going to be open sets, because you know they look like, for example, u0 is first homogeneous coordinate not vanishing, okay. u1 is second homogeneous coordinate not vanishing, ui is ith homogeneous coordinate not vanishing, and whenever a coordinate does not vanish, that should be an open set, okay. So you must you can see that these are going to be the open sets, okay. But then let's not worry about them as open sets, you know. Well, in fact, I can say that, you know, if you take the inverse image of this ui, okay, under this map, then I am going to get the complement of the 0 set of xi, the ith coordinate. In fact, I should call it I plus 1th coordinate, because I am starting with 0. My numbering starts with 0. So you know, if I take this ui and take the inverse image above, what I will get is, I will get all the points with the I plus 1th coordinate not 0, okay, and that is the, I will get that set inside the punctured affine space, and you know its complement will be all those points with I plus 1th coordinate, I mean with that coordinate 0, which is of course a closed set, okay. So the inverse image of ui under pi is certainly an open set, and therefore you know this is certainly open according to the definition of the quotient topology, okay. I mean according to the definition of the quotient topology. It is also open according to the definition of this indigenous Zariski topology, because it is actually the complement of the 0 locus of that coordinate, where that coordinate is considered as a homogeneous polynomial of degree 1, okay. See, so note that pi inverse of ui is actually z, it is an plus 1 k minus z of xi intersection with an plus 1 k minus the origin, okay. This is what it is. This is actually what? This is just dxi. It is this. So the complement of the 0 set of xi is the basic open set defined by xi, alright, and that is an open set, and if you intersect it with this subset, it will give you an open subset of this, okay. So this is which is open in the punctured affine space above, of which the projective space is a quotient, okay. So you know, according to definition 1, this is an open subset of the projective space. If you give it if you look at the quotient topology, then this is certainly an open set, okay. And what you must understand is that you see all these ui's I equal to 0 to n, there are n plus 1 of them, and they cover the projective space, because when you write a point with projective homogeneous coordinates, all coordinates cannot be 0, because you have thrown out, this is the image of a point on the punctured affine space above, okay. So you are not so all the coordinates cannot be 0, right. So whenever you write homogeneous coordinates, at least one coordinate is not 0, which tells you that therefore that point lies in one of the ui's. So all the ui's, these n plus 1 ui's, they are a cover for the projective space, okay. And according to this definition, if you give the map pi the quotient topology, then these UIs are open, okay. According to this definition also it's open, because you see, note also that if you take away UI from Pn, what you will get is of course the 0 set in Pn of the homogeneous polynomial xi. See, you take the polynomial xi, okay, that is of course homogeneous polynomial, it is homogeneous of degree 1, alright. So by definition its 0 set should define a closed subset of projective space, and therefore its complement, which is precisely UI, is open, okay. So this UI is open according to this definition, it is also open according to this definition, alright. Now further, all the UIs, union of all the UIs I equal to 0 to n is actually Pn, of course. The projective space is covered by these sets, okay. But the third topology on Pn is something that I have not yet defined. But I need these UIs to define it. So what I am going to do is, now you take this UI, which is the set of all homogeneous coordinates, points in Pn such that the ith coordinate is not 0, which is subset of Pn, and what you do is you define a map like this into An, okay. The point is that each UI is automatically an affine n space. Each UI is actually an affine n space, okay, and beautiful thing is its complement, which is Zxi, is a projective space of dimension 1 less, okay. So the beautiful thing is that each of these UIs is actually an An, okay, and its complement is a Pn minus 1, alright. So let me explain that, and that complement Pn minus 1 is called the hyperplane at infinity, okay. So let me explain that. So you know, this map is very easily defined. So what you do is you take a point with coordinates lambda naught, etc. So I will write this down. There is a lambda I minus 1, there is a lambda I, and then there is a lambda I plus 1. I won't write lambda I plus 1 because it might be the last. Then lambda n, okay. And you know what I am going to do? See, I know lambda I is not 0, alright, and you know the homogeneous coordinate is not going to be affected if you know, I multiply the whole set of homogeneous coordinates by a non-zero number, and what I am going to do is I am going to just multiply it by 1 by lambda I, which makes sense because lambda is not 0, alright, and then that will give me a 1 in the ith position, okay. In the place of lambda I will get a 1. So what you must understand is that this is the same as, well, let me write this, it's lambda or not by lambda I, lambda 1 by lambda I, blah blah blah. Here I will get lambda I minus 1 by lambda I, then I will get a 1, and so on. I will get a lambda n by lambda I. These two ratios are one and the same point on projective space. That's because this is just this multiplied by the same lambda I, which is a non-zero element of K, okay. And but then you see this point 1 is I mean this 1 is redundant, so what you do is you get only the remaining n distinct scalars, and these are the n scalars to which I mean these are the coordinates to these define the coordinates of the point to which you are going to send it. So what you are going to do is you are going to just send it to lambda naught by lambda I, comma lambda 1 by lambda I, and lambda n by lambda I, where you know the way I have written it is you omit lambda I by lambda I, which is 1, okay. So this is n plus 1 entries, I omit that 1 and I get n entries, okay. Now because of the way I have defined it, you can check that this is a bijective map. This is a bijective map. That's the reason is because the moment one of the coordinates becomes 1, you see then the other coordinates are unique for that given line, because if you try to change by a scalar, okay, then this you can't change it by a scalar without changing the 1 to something else, okay. So if you freeze the ith coordinate as 1, then the remaining then for each line for which the ith coordinate is not 0, okay, if you rationalize so that the ith coordinate becomes 1 for a representative point on the line, then the remaining n coordinates are unique. So the fact is that this is a bijective map. So I know, let me call this as phi I. Phi I is a bijection. This phi I is a bijection, and of course it's a bijection. Why is it surjective? Well, phi I is injective. It's injective and surjective for the reasons I just said, but anyway, let me, if you want, you can write it down. It's not a big deal. If you have, if phi I of one point, a given point lambda naught through lambda n is equal to phi I of another point mu naught through mu n, then so this will imply that lambda naught by lambda I, etc., lambda n by lambda I is the same as mu naught by mu I by mu I, and so on, un by mu I, okay. And what this will tell you is that it will just tell you that lambda naught, so it will tell you that lambda naught is lambda I by mu I into mu naught. So each lambda j is lambda I by mu I into mu j, and this lambda I by mu I is one the same, it's fixed, I is fixed, okay, lambda is fixed, mu I is fixed, okay. Therefore this quotient is a fixed scalar, and what you are saying is that every lambda is a fixed scalar times every mu, the corresponding mu, and that means that these 2 points define one and the same line. That means they are one and the same point on projective space. So this implies that these 2 points are the same. Okay, this is just injectivity. I mean, and of course surjectivity is very simple again. Why is that? So you give me a point in affine space, a point x1 etc. xn in an is phi of, well, I can write this point, you know what, I am just going to put I put x1 etc., and then I put a 1 in the ith position, and then I put, of course I have to put colons here because this is just homogeneous coordinates. So if I take this point will go to the point I started with, so it's surjective. So if you want to map from here to here, you simply write these coordinates in the same order as n plus 1 entries, homogeneous coordinates, but put don't fill the ith position. In the ith position you put 1, the remaining n positions you put these in the same order. That's the map in the reverse direction. Therefore these phi I's are all bijective maps. The phi I's are all bijective maps, and the fact is that now what I can do the following thing. So in very much the same way in which you get a manifold by getting local charts into Euclidean space, you think of trying to make projective space you know in a sense like a manifold by taking these as local charts which identify these essentially open sets with affine spaces. So you think of so in other words I am saying that I am saying use these phi's which are bijective maps to transport the topology on the affine space back to UI. See, each copy of affine space has a topology. It is a Zariski topology. So I can simply transfer the topology here. Namely, what is it? You give me a subset here. A subset here is open or respectively closed if and only if its image here is open respectively closed for the Zariski topology on this affine space. Okay. So with that definition, also I can give you a topology on each UI. Okay, and the UIs cover of course cover the affine space, and the only thing that you will have to worry about is whenever there is an intersection the topologies agree. Okay, so that will happen. Okay, that is analogous to the compatibility of charts which involves the transition functions being good. Okay, and in this case the transition functions will be just xi by xj. Okay, and therefore what will happen is that you will get a good all these topologies on each UI which are transported via the phi. So each of these topological spaces UI, they will glue well on the intersections UI intersection uj to give a unique topology on Pn. Okay, and that is yet another topology on the projective space. Okay, which comes from via the gluing of n+1 copies of affine space. These n+1 copies of affine space are given by the UIs which have been identified with the corresponding affine spaces via phi's. Okay, so so there are and the big deal is that the big deal here is that that all these topologies agree on the intersections. Okay, that is a very important thing. So if you have a topological space, okay, and suppose you have two, if you just have a set, okay, and if you have two subsets, and suppose on each subset I give you a topology, alright, then on the union of those two subsets this will give a topology provided on the intersection the topologies should agree. Okay, the intersection a set in the intersection considered as a subset of one is open if and only if it is open with respect to when it is considered as a subset of the other. Okay, so if you have two subsets of a space of a set, you give them topologies separately. Okay, then when do you get a topology on the union? You will get a topology on the union only when on the intersection the topologies agree, that is a subset of the intersection is open respectively closed in one if and only if it is in the other. Okay, this is the situation for two sets, but if you have a collection of sets for example even a collection of subsets which is a cover for the given set, on each subset if you give me a topology, when will all these subsets glue together to give a global topology on the set? That requires a compatibility. Okay, it requires a compatibility that whenever you take a certain sub collection of subsets and you take their intersection, a subset of that is open if and only or closed if and only if it is so in each topology coming from the corresponding members. Okay, so and the fact is, that is a big fact, the fact is that all these topologies on each UI, okay, which come from the Zariski topologies on affine space, they all glue together and give you a topology on the projective space. This is the third way of getting a topology on the projective space, and the fact is all the three are one and the same. Okay, so there are three ways of giving a topology on projective space and they are all the same. Okay, now what I am going to do is so let me write that down. So maybe I will write it here. So I will write here give each UI a topology by declaring phi to be a homeomorphism that is a subset W in UI is open respectively closed if and only if phi W phi W in AN is open respectively closed. Okay. So if you give this topology to UI via phi, then it becomes, it's automatic that this phi becomes a homeomorphism of UI to affine space. Okay. So you know what you're doing is, for every point on this UI you are giving me you're just taking n affine coordinates. Okay. So each one is a coordinate map, each one should be thought of as a chart, the analog of a chart for a manifold. Okay. So each one is a coordinate map, alright, and what we are saying is that once you have a manifold structure, each chart in the atlas, if you take the corresponding coordinate map, it is of course a good function, it is of course an isomorphism. Okay. So in this case what is happening is we are gluing topological spaces, all the UIs are glued together to give the topology on PM. So the topologies on each UI agree are compatible on the intersections and define a topology on Pn. And for that topology on Pn, when do you say a subset of projective space is open or closed? It is open or closed if and only if its intersection with each UI is correspondingly open or closed in that UI. And how do you check it? You check it by taking its image under phi and see whether the set you get in the corresponding affine space is open or closed. Okay. So so this has to be checked, that you have to check that the topologies on each UI they are all compatible, alright. So for example, if I take two different UIs, UI and UJ, it should not happen that a subset of UI intersection UJ is an open subset of UI and is not an open subset of UJ. Such a thing should not happen, it will not happen, that is the compatibility you have to check. Okay. So in other words, UI intersection UJ has a topological subspace structure from UI, it also has a topological subspace structure from UJ, and my claim is that these two are the same. Okay. That is what has to be checked, right. It only if you check that, then you are saying that these topologies glue together to give a global topology on the ambient space, which is the full projective space. Okay. And what is a big deal? The big deal is whether you use 1, 2 or 3, the topology you get on projective space is one and the same, and that is the Zariski topology on projective space. Okay. So so let me write that down. Fact so here is a fact, it needs a little bit of checking, that it's pretty easy to do, you can try it out. Fact or theorem if you want, or each of these ways, each of these 3 topologies on Pn is the same as the others. That is a fact. Okay. So so what you must understand is that all these phi's are actually homeomorphisms. So if you think of projective space with the Zariski topology, if you think of this as an open subset, and you take the induced topology, then each phi is automatically homeomorphism, okay, by this fact, by this theorem. Alright. Now so this is something that I leave it to you to check, but probably portions of it we will check as we go ahead. Now what I've got to do is I want to, the purpose of course this course is to translate from geometry to algebra and back, okay. So all this that we have been saying is more or less completely geometric and topological, but then to go to the commutative algebra side we will have to worry about the polynomials that are involved, okay. And you know that that's where the second definition comes in, the second definition which says that the Zariski topology on projective space is given by taking the closed sets to be common zero loci of a bunch of homogeneous polynomials in the right number of variables. The number of variables will be one more than the subscript, the superscript appearing in the projective space, okay. So we have to study these homogeneous polynomials. So for the first question is why homogeneous polynomials, okay, and then that will lead to looking at the theory of homogeneous ideals, okay. So the fact is when we did just like when we did translation from the Zariski topology in affine space to the polynomial ring, we were worried about ideals, okay. We'll when we do study Zariski topology on projective space, you will also have to translate everything to ideals, but the only thing is the ideals now will be so called homogeneous ideals, okay. And one way of thinking of homogeneous ideals is that these are ideals which are generated by homogeneous polynomials, okay. So first of all I want you to realize that the homogeneity property it can be defined in more than one way, and to explain that let us look at an example, okay. So suppose you take suppose we take a point lambda naught lambda n in projective space and let f x naught through xn vanish on the line through lambda naught etc lambda n, which is actually this point, okay. The point in projective space is the same as its inverse image, which is the line, okay. So well the way I have written it is that when I say that this point on projective space corresponds to this line can also be thought of as living, it's actually being thought of as living above. So actually this the inverse image of this point is this line thought of as a line above, okay. Here you are thinking of the line as a point here, okay, but if you think of it as a subset of an plus 1, okay, then the inverse image of this is this line itself, okay. So pi inverse of this point is actually the line through lambda naught lambda n considered as a subset of an plus 1, right, that is what it is. So you get another nice picture of this whole of this map. You get the picture of what is called as a line bundle. A line bundle is something for which you have a map from one topological space to another topological space. For every point below, the inverse image is a line above, okay. So you think of this as a bundle of lines above this, and what is every line above goes to the corresponding point it represents in the projective space, okay. So you think of this fibration, as it is called, as a it is thought of as a it's sort of as a line bundle. You think of given a point here corresponds to a line above, a line through the origin above, and what is that line through the origin above in terms of the point here? It is, well, if you take the inverse image of this point, that's exactly that line above, okay. That's what I've written here, alright. Now you see see if the polynomial vanishes on this line, okay, what it means is, so this implies for every t which is a non-zero scalar the field, okay, well f of t lambda naught etc t lambda n should be 0. This should happen, right, because you see I have told you that the so you know if I draw a diagram, here is my projective space, okay, and I have taken a point here with homogeneous coordinates lambda naught through lambda n, and under this map pi I go to the affine punctured affine space above. What I get is, well, I get the line through lambda naught etc lambda n minus of course the origin, okay. So if I take pi, this is what, so pi inverse gives me this inverse image, do not confuse pi inverse for inverse map. I get this line, of course the origin is thrown out because I am considering it as a subset of the punctured plane. Then you see when I say the polynomial vanishes on this line, it means that it should vanish at every point on that line, and every point on that line looks like this, okay. But then you write this out you write this out, what it will tell you is the following. Yeah, so I should here also when I say pi inverse of the point is this line, I should say this line minus the origin inside inside the punctured affine space, because pi is not defined at 0, alright. So this is the right way to write it, but you do not worry about the point at 0 which has been intentionally removed, okay. So well, so in any case, now you see you write this polynomial f of x naught xn, you break it down into its various homogeneous components. You see a polynomial in n variables can be broken up into pieces, a sum of pieces, each of which is homogeneous of a particular degree. So there is a degree 1 term which will be linear expression in the xi's, okay. Then there will be a degree 2 term which is a linear expression in product of 2 xi's, namely it will involve xi squareds and you will get xi xj, okay, and so on you will get. So the polynomial breaks down into f naught x naught etc xn. This is degree 0, so this is actually a constant, this is the 0th, this is the constant term of the polynomial which is what you will get when you put everything 0, okay, plus I will get f of f1 which is degree 1 term, which is degree 1, this is the linear term, okay, then and I will get it and I will go on like this, and I will get fd which is the degree d term, this is the degree d term, and of course when d is 1 it is linear, d is 2 it is quadratic, d is 3 it is cubic, and so on and so forth, and so on you go on up to f to the degree f. This is the highest degree of the polynomial, okay, it is a degree of the highest weight monomials that occur, okay, and the point is that each of these guys is homogeneous of a corresponding degree. So if you take fd, this is homogeneous of degree d, f1 is linear, it is homogeneous of degree 1, alright. And now you know let's look at this condition, f of t lambda naught through t lambda n is 0 for every t non-zero. So what it will tell you is 0 is equal to f of t lambda naught t lambda n. That will tell you that, you know, when I plug this in I will get, well, this will just remain f naught t lambda naught t lambda n, plus when I plug t lambda naught through t lambda n here, then t will come out because it is degree 1. Similarly when I plug it in fd, t power d will come out because it is homogeneous of degree d, so the expression will look like t times f of lambda naught etc. lambda n plus t squared f of lambda naught etc. lambda n and so on t to the d f of lambda naught etc. lambda n plus blah blah blah, you will get t power degree f times f of lambda naught etc. lambda n. This is what you get. You get for every t not equal to 0 in the field, okay, you get this expression. Sorry, yeah, I should put, sorry, you're right, I should put f1, should put f2, fd, this is f sub degree f. Yeah, thanks. These are not, they should not be f, they are the corresponding homogeneous components. Thanks. Yeah. So this is t times f1 t squared times f2 t power d times fd and so on. Okay. Now you know, I want to I claim that this implies that you know I claim that this implies that each fd of lambda naught etc. lambda is 0 for every d greater than or equal to 0. Okay. I claim that each fd vanishes and so fd of t lambda naught etc. t lambda n also vanishes for all t in a scalar which is non-zero. This is my claim. Okay, you know, see, therefore what I am trying to say is that if a polynomial vanishes on a line, then each of its homogeneous components also vanishes on that line. Okay, each of its homogeneous components also vanishes on that line. Okay, that is what I am trying to say, and this is the key to defining a homogeneous ideal. All right, and why is this true? Why this is true is because, you know, let me call this as scalar as a naught. After all, this is scalar. Of course, here this is independent of t because this is a first term, it is constant. So let me call this. So what I will get is I will get a naught plus t a1 plus t squared a2 plus t power d ad and so on up to plus t power degree f a sub degree f is 0. So I will get a polynomial in one variable, okay, with these coefficients, k coefficients, and what I am saying is that that polynomial identically vanishes on the affine line minus the origin. Okay, but you know, if a polynomial vanishes on an open set, it vanishes everywhere. Okay, if a polynomial is 0 on an open set, it is 0 everywhere. That is just because of continuity of the Zariski topology. Therefore, and of course, mind you, here is the first place where you are using k is algebraically closed because I want k to be an infinite field. Okay, so probably I don't. Okay, I need k an infinite field. All right, for that. So I am just saying the fact that you have a polynomial in one variable. You know, if it vanishes on an open set, okay, then it is identically then it's identically the 0 polynomial. So therefore this polynomial is identically the 0 polynomial, therefore every coefficient is 0. That is exactly what I have written here. Okay, so the moral of the story is, I want you to remember this is the key fact defining what a homogeneous ideal is. The fact is, if a polynomial vanishes on a line, then each one of its homogeneous components that also vanishes on the line, and in particular it is a non-constant I mean the constant term is 0 in particular. The constant term cannot be non-zero, the constant term has to be 0. Okay, so so this is the point I want you to remember when we go to the next lecture, right? So I will stop here.